Let's get started. So today we'll be going through lecture 18 lecture 18 content. We still have 2 more lectures to go, and this lecture is about 3 recursive neural networks. To be honest, after going through the lecture, I tried to find some resources on this topic, like 3 neural networks, and I didn't really find much. I didn't find any Medium blogs or anything of that sort on this topic. So we'll quickly run through the slides, and then we can have any discussion if anyone has anything to share. So let's get started. The first slide is about some plan. Yeah, so this is a lecture plan. We'll get started by looking into what compositionality is and recursion is. Recursion must be familiar to you if you're into programming. And then we'll see what a simple tree recurrent neural network looks like. And there are different variants of it. We'll look into those as well. And yeah, so let's go to the main slides. Yeah, so for the most part of the lecture, especially in the beginning of the course, the things that were mostly discussed were based on word embeddings. That's what we had like in the first few lectures, and then somewhere in the middle of the course, we also discussed what character level embeddings are. So, and we have discussed how character level embeddings provide few advantages over word level embeddings, especially in handling out of vocabulary words. So even with those 2 options, we can see that we are pretty limited to either word level or character level embeddings, which means we only have representations for word level and character level, but not anything more than that. So getting a meaning or the word representation for larger phrases or phrases like group of words is a challenge. Now, for us humans, it is pretty intuitive to make sense of these 2 sentences. The snowboarder is leaping over a muggle. A person on a snowboard jumps into the air. So for a machine to understand a sentence like this, we have to break the sentence into individual words, and then every word has its own word representation. So that's how we break it down. So for people, the way it works is that we pick the entire sentence, and then that gets like intuitively we decompose things into smaller things, and we put them together and make sense of the entire sentence. Like in this case, a person on a snowboard jumps into the air. Like different parts of this single sentence convey some different meaning, and the way we make an understanding of the whole sentence is by breaking it down to different things. Like a person, okay, we know we're talking about some person on a snowboard. Okay, so there is a snowboard here, and there's an action which is jumping into the air. So that's how we make sense of this whole sentence, by doing something called semantic composition of smaller elements. So we're talking about compositionality here. So does that exist only in language, only in when we're talking about sentences? Actually, no, we have it everywhere. Like even if you're talking about some machinery like this, let's take a car engine or something like that, even that has compositionality, because whenever we have something, it's nothing but it's built from much smaller components. And we have that in vision as well. So to make sense of an image like this, though it happens pretty fast, what actually happens here is that we make sense of this image at different levels. We know that we see people. Okay, a certain part of the image has people, and we also see some tree, and then there is some building, some church or structure here. So as you can see here, the entire image here can be decomposed or can be broken down into much smaller components like this. We have trees, we have people, and then we have different parts of this building or structure here. So compositionality exists in language, it's there in vision as well. And yes, so making sense of smaller things, putting it all together, and then making sense of the entire thing is very critical both for language understanding and for artificial intelligence. So here is some paper reference. It talks about several things like how uh, linguistics is more like language is more of interdisciplinary cooperation, like it needs understanding of several other things and we put them together. But what's interesting here is that there's a mention for recursion here. So what this paper talks about is that for us to understand a language, for us to understand something that is spoken, uh, there is recursion involved in it. So what is recursion? So normally when we're talking about recursion in programming, we know that when a function calls itself, it's a recursion. But what exactly happens when a function calls itself? What happens is that the function gets broken down into smaller parts. Like if you want to find let's say if you want to find uh, something like a Fibonacci number or something like that, and when you want the 100th number, you actually get to the 100th number by getting the numbers which are below that. So that's how you build your final answer. So that's what recursion is. When you have a problem, you break it down into smaller problems, and that would essentially give you that tree kind of a structure, which looks something like this. So recursion is natural when it comes to language. That's because, as we can see here, we have a whole sentence like he eats spaghetti with meat, something like that. And each sentence here, like each word or group of words in this sentence here can be put together to form some specific component. Like as we can see here, we have noun phrases, we have prepositions, we have a verb here. So putting all of these things together, we are able to come up with this example. So the example here, what it means is that this entire sentence itself is like it has a noun phrase, and it also has noun phrase within another noun phrase. That's what these braces indicate here. Each of these, the man from is a noun phrase, and then we have another noun phrase, the company that purchased. So this way we have these nested kind of noun phrases. This again is something like recursion. Here's something called tree branch, giving another example. So yeah, so this is a word vector space. This is nothing but when we have something like word to vec, every word has its own representation, which is nothing but some d-dimensional vector. And if we plot that on some vector space, we get these kind of representations. So what we have is we only have word representations for characters or for words, but not really for phrases or for larger sentences. So now let's say when you want a vector representation for a word like Germany, you can get it something like this. You have a representation for Germany, for France, for Monday, and for Tuesday. And as we can see here, these are countries, and they are at one end of our vector space. And then we have weekdays here, which are at some other corner of our vector space. So what these word embeddings do is when we plot them on some vector space with some dimensionality, they kind of cluster the related things together. As we can see here, the countries are all being clustered together at one part of the vector space. And then we have another semantically different things like weekdays, which take up a different part of the vector space. So this is good for words, but how can we get such representations for something which is bigger than words, like phrases and longer phrases? What if we want to represent something like the country of my birth? That's a sentence, and we want a representation for that. Or for another example sentence like the place where I was born. So that can be done using principle of compositionality. So there are two things here. One is the meanings of the words of the sentence, and also the rules that combine them. So if we have to find a vector space representation for a given phrase or a sentence, these are the two things that have to be considered. Like every sentence has its own set of words, and the meanings of those words have to be preserved. And also, given a set of words, there are some rules that needs to be followed. Like there are some semantics and syntactic rules that need to be followed. So if these sentences are to be encoded into some vector space or representation like this, these two things have to be considered. So as we can see here, one way of doing that is this. So normally this is how a tree structure looks like. So we have, normally when we're talking about a tree structure, we start at the top, we have a root, and we have the root node here, and it has two child nodes. So that's how a generic tree structure looks like. But in this case, we start at the bottom. We have our words, the or our input or the sample example sentence, the country of my birth. And what we're doing here is, as usual, we get started by getting the word embeddings for every word. So the word the has its own word embedding, and the same goes for the other words as well, like country of my birth. And what's happening in the next level is that depending on some, like here, the two words the and country are being combined together to form this representation, because the and country together form a noun phrase. And then we have my birth, that's another noun phrase. And then we have a preposition that is being added here. So this and the representation for my birth are being combined together like this. And finally, we get 1 5, which actually represents this whole phrase. And that gets plotted here in the vector space. And the same happens for the other example as well, the place where I was born. So as we can see here, when we're doing this, both of these sentences are somehow related: the country of my birth, the place where I was born. So these two sentences, though they might be different, they are kind of similar, because they're in a way talking about birth. And as we can see here in the vector space, they're actually placed pretty close to each other. So this is what we're doing. So we have another sentence here: the cat sat on the mat. So the cat, these two words together will form a noun phrase. And then we have another noun phrase here, the mat. Then the mat, when combined with on, gives us I think it's a prepositional phrase. And then that gets added with sat, which is a verb, that would give us a verb phrase. So this way we are putting together two or more words and forming different semantic components, and putting it all together, we get our sentence or the phrase. And this way we get a representation finally at state S, or the node S will give us the uh, representation for this entire phrase or sentence. So what's happening here is that the whatever it is, the model here needs to learn both the representation for the sentence and also the structure. So as discussed before, we need to retain the meaning of the words or the sentence, and also we have to retain the structure and the rules that needs to be obeyed by different combinations that are allowed. So as we can see here, that's what is happening. So here's a comparison between how the structure of a recurrent neural network looks like, and uh, uh, above here we have the structure for recursive neural network, and below we have the regular recurrent neural networks. So let's quickly see this recurrent neural network. What's happening here is that we have the same words, the country of my birth. For every word we have our word embedding, and that, let's pick country here. So country has its own word embedding, and this is being given as the input for this state. And this hidden state takes two inputs. One is the current input towards word representation and the output from the previous hidden state. So putting these two things together, it computes its own output state, and the hidden state value is computed and it is passed to the next state. So this is what we have when it comes to the recurrent neural network. And the same thing, when it comes to recursive neural network, we have the words here. And what's happening here is that we have the words which are being clubbed together depending on how, like the country, again, it's a noun phrase. So here we have these two words. Those word embeddings are taken and they are being taken together to get a representation for the phrase the country, and the same happens for the rest of the words as well. So this is how the structure of a recursive neural network differs from that of a recurrent neural network. So the recursive neural nets require a tree structure, as we can see here. So why do we really have to worry about a tree structure? What actually is the problem that we are trying to address here, that we have with recurrent neural networks, which can be addressed using the recursive neural networks? One thing is that, as we can see here, the input for every state in a recurrent neural network is nothing but the input word for that specific timestamp. It doesn't really put together the words. It doesn't really put together the words. It only takes them one at a time. Though the way the hidden states work, let's say when by the time we are giving the word my as the input to the model, whatever the input that this hidden state gets from its previous hidden state, that state does contain some information about the words that the model has seen so far. So that information is encoded into it. Though that's there, it still doesn't consider capturing information that comes from phrases or like more than one word being put together. So that's what can be addressed using recursive or the tree neural networks. So there are two things here when it comes to recursive or tree neural networks. One is the semantic representation of the nodes. Like in this case, we have, let's pick, so we have the words, the phrase on the mat here. We have the word embedding for the word representation for each of these words. And as we can see here, the and mat are being merged together. That's a noun phrase. And then the result of this is being merged with on, which is a preposition, and that would give us a preposition phrase. So that's what is happening here. And what happens if we have to try to visualize that as a neural network, we have 8.5 and 3.3 here. 8.5 is the word representation for the word on. 3.3 is the representation that we got by merging two words, the mat. So unlike the traditional way of doing it in neural networks, where a neural network gets its input from every word's word embedding, here the input that is being given to the neural network is slightly different. It gets the word representation, the vector representation for the word on, and then it gets the vector representation for the phrase the mat. So that's how it's kind of different from recurrent neural network. And then what it does is, if so normally when we're talking about word vectors, what we want to do is given a word and another word, we would like to know what is the probability or score of these two words going together. Like when we're talking about language model, given three words, like the cat sat on the, this is the example, and if the model has to predict the next word, it would generate higher score for words like the cat sat on the table, chair, or something like that. For these words, there would be kind of high score. And for the words that are not that probable to fit in this example, they will be having uh, lower score. So here, even in this example that we are seeing, when we are trying to merge different words or a word with another phrase, the model has to predict what is the score for these two things to go together, because as we mentioned before, we not only want the words to be merged, we want the words to be merged only when they are semantically possible, like when they retain the grammar rules that needs to be followed by the language. So here in this example, it is taking these three words together, and then it is not it is generating two things. One is the final representation for this phrase, and also a score saying 1.3, that the word on can be merged with the phrase the mat. So internally what happens is, as usual, we have our weight matrix W that gets multiplied by the input, and then we have the bias term. Tan H here is our activation function. So here's another example, like the same thing, but with more states. We have different words here. We have their word embeddings or representations, and then here we are merging, like we have the and cat going together, and we have the scores that are being generated for each of these, and that finally gives us something like this. So the score that we are seeing here, that is actually computed by taking the total of all the decision scores at each node. If we can think of each of these as nodes, like normally when we are talking about tree structure, we have we have certain number of layers where each layer has its own nodes. We have something very similar here, and every node has a score that is generated, and the final score is generated by taking the sum of all of those scores for each of those nodes. Yeah, so similar thing happens with scene parsing as well, like principle of compositionality, that's what it's called. Uh, the scene image, the meaning of this image is nothing but a function of the meaning of the smaller regions or the smaller components that we can see in this image. So there are two things here. One is making sense of smaller parts in the image. That is, we have people here, we have tree, and then we have some structure here. And we should also know how to correctly put things together. Like if we have two smaller components which have people, they can go together, but it's not like the people can overlap with a part of this structure. So that's what it means when even when it comes to language, we have two things. Like we need the meaning of the words, and also we need to know like how to properly put them together, following the rules. The same thing goes with vision as well. So here's another representation for that, the tree sort of representation. So so segmentation, like normally when you're trying to do object detection, there are two ways of doing it. Like you give your model an image, and then the model kind of detects what it sees in the image by drawing bounding boxes on the image. But segmentation is slightly different, where it gives more fine-tuned detection. As we can see here, different entities in the image are given different colors. Like there are vehicles here which have a different color than the buildings. We have trees which are uh, labeled in green. So uh, so that's what is happening here. We have an entire image, and then we have different components in it, like smaller components. We are putting like, if you have read about segmentation, like instead of just saying this entire region by a bounding box contains a car, we actually label those specific set of pixels where the car is seen with some color. So this is something that we can relate to with this. So again, we have backpropagation here. Without that, there is no learning, and there is the model wouldn't be learning anything. But the way it works is slightly different. What it does is all the derivatives of all the weights from all the nodes are taken, and their total is taken. And whenever there is a split from a parent node to the child node, the derivatives are also split, and the error messages from parent to node are added. Here there is the math representation for that. Any questions or anything that you would like to add?
I have a question.
Yeah.
So the scores in both natural language and in image understanding, are they also computed by network training?
You mean whatever we have seen so far?
Yeah, no, like so in this approach in recursive neural network,
yeah.
So he has neural network basically calculating the node values and the score.
Mm-hmm.
And you said score is basically likelihood that those things go together. So is score also basically so score, after you train neural network, basically score is another result that will come out, right?
Yes, exactly. That's right.
So normally I would assume you would train this on real sentences, right?
Mm-hmm.
So and if real, like this is what I don't understand. Like so, if you train this on real sentences, then and you say score represents how likely, how natural those things go together, that all scores should be high, because if somebody wrote it and it's grammatically correct and it's it's a correct sentence, and then
yeah. Yes.
So what kind of so we summed up the scores. Is that used? Some of the scores used then for like I don't think when I was listening to the lecture, I didn't get this at all. So I think your explanation is much better. But I'm still not sure. Like so let's say we trained it. How do we use it? How do we use sum of scores?
Okay. So if I understood your question correctly, now let's say normally for like when we're training a model, we give it some input, and then the model learns something, and then when we give it some other data, it has to work on it, right? So here in this case, going by this slide, as we can see here, we have the words here. Let's ignore for a while that we are talking about something different here. Let's ignore about tree or recursive neural networks. What we have here is, let's pick one thing here. the cat, right? And we have word representation for both of these words. And since we know that these two are like, they can be put together because they can form a noun phrase, and they're being merged to give us this representation. And then what's happening here is that this and the verb sat are being fed to a neural network, and this neural network, it will generate a representation for this, for phi2 and 7.1 together. In addition to that, it also tells us, how probable it is for these two things to be merged, like for them to exist next to one another in a sentence.
Mm-hmm. Okay,
Yeah.
so let's say we train this neural network. And actually, one thing I
Mhm.
didn't understand. So I understand with recursive neural network, you basically have the same weights, right? And you keep training them. Um,
Yeah, so
those
we
all
do.
those Yeah, go ahead. Like all those networks, they like structure of the sentence is arbitrary. So like, is it the same? Is it the same network that puts, like, let's say, those two nodes together?
Yeah, so when it comes to RNNs, the regular recurrent neural networks, we have the weights that are shared, and
Okay.
also the dimensionality of the weights don't change. But
Mm-hmm.
here, the weights are they are slightly different. We'll see why it is like in the in the coming slides. But
Mm-hmm.
yeah, the way the weights work, the dimensionality, and as you said, the way they are shared, that part is different from how we have it in recurrent neural networks.
Okay. Okay. Thanks.
No problem. So even for me, like when I was going through the lecture, like there were many parts of it that weren't really that easy for me to understand, and I tried to find some resources to get a better understanding, but I hardly found anything. I must say. Okay, so let's continue. Yeah. So when we have a simple tree RNN like those that we have seen so far, here are some points about that. Uh, what we talked about so far, it is a single weight matrix, and we'll see how it is different. We'll see how what its variant is. Though these tree structure help us in capturing information more than a word, like as we have seen, we can put together like different words and different phrases together and feed them to the model. In that way, it helps, but still, it's not really that good when it has to parse pretty long sentences. And whatever the composition function that we have, like whenever we are merging something, it's whatever we have seen so far, there is actually no differentiation for different syntactic categories of punctuation. So whatever the words or the inputs are, they're being merged using the same composition function. Uh, so we can that can be changed by trying like different composition functions for different words depending on the kind of syntactic component they belong to. We'll see what that means. Mm. Yeah. So a tree RNN can do better with different composition matrix for different syntactic environments. So instead of having the same composition matrix, like when we are merging different words, instead of having the same composition matrix for all the words, maybe we can have different composition matrices for different components. So this compositional vector grammars, it, the problem with this is that like whatever the candidate scores that are being generated, they need a matrix vector product. So as we have seen, in addition to generating the vector representations, we also have the scores that are being generated. that score generation is computationally expensive as it involves a matrix vector product. So that's one problem. And the solution for that is like using pruning. Like if the model feels that if there is a candidate which is unlikely to happen, maybe it can prune it. Here are some works on parsing. Here are some experiments that are done. As we can see here, these two are related works, composition vector grammar. And this book has been done 2013, it says, but I haven't really heard much about tree or recursive neural networks outside this course. Okay, so here are some examples. So if we are taking the vector representations that are generated by these tree or recursive neural networks, these are the results that are found. Like each sentence in blue is an example. And there are two sentences that are reported here, which are like, this is nothing but previously we had weekdays, Monday and Tuesday. We have seen that when we have plotted them in vector space, they are together at some, they are close to each other. So when the phrase or the sentence representations are taken that are generated from the tree neural networks, these are the results that are found. When the input sentences, all the figures are adjusted for seasonal variations, and the two closest sentences that are found for this sentence are these two. Like all the numbers are adjusted for seasonal fluctuations, all the figures are adjusted to remove usual seasonal patterns. So as we can see here, we can see that the two sentences that are given here, they are kind of related. They are similar to the to this sentence, and the same goes with the other examples as well. So this shows that generating the vector representations using the recursive neural network generated embeddings, it is actually doing a decent job of putting together things that are similar to each other. Yeah, so we have a weight matrix here, and there's something called untying the weights. So what exactly does that mean? Here we have a slightly different representation. So we have the words very good movie. Normally for every word we have one vector representation, but as we can see here, for every word we have two representations here. One is a vector and the other one is a matrix. So this is another variant of it, which is called recursive matrix vector model. How this is different is that for every word, you not only have its vector representation, but there is also a matrix representation for every word. And the reason why they're doing this is that there has to be some sort of differentiation when you're using the word very as an operator. Like here, you're trying to, like, good is different from very good. Like when you're adding the word very in front of good, it's like you're trying to convey something more about the word that follows next. So in order to encode that sort of information, like for every word, you also have a matrix which contains some other information in addition to the regular vector representation. Mm, yeah, and
what's the dimension of this matrix?
So I'm not sure, but it is huge. When compared to the dimensionality of the vector, these matrices are actually much bigger. And that's one problem that we have with this approach, because like normally when we're talking about vector representations, let's say we have something like 128, 256, 512 dimensional word vectors, right? Or even 1024. That is comparatively okay when we compare that with these matrices, because these are like these are much bigger than in terms of dimensionality, these are much bigger than that of the vector embeddings.
So they're in the like sort of original word space.
I'm not sure about that.
Okay.
Yeah. So whatever we discussed, that's called matrix vector RNN. MVRNN here stands for matrix vector recursive neural networks. So here, so here's one task called semantic relationships, which is an NLP task. So the question is, can an MVRNN learn how a large syntactic context conveys a semantic relationship? So here we have the example, my apartment has a pretty large kitchen. And what we're looking at is a component whole relationship between the words apartment and kitchen. So this is how it is. So this is one example of a task on which this model is used. And we also have somewhere, I think, sentiment analysis. I think that comes later, yeah. So we have different variants of it. That's what we are looking at. We started with the plain tree recursive neural networks, and then we had these different things that are being added. We have this matrix vector RNNs, and then we have something called recursive neural tensor network. So less parameters than MVRNN. So coming back to the question that was just asked. So as we can see with that, with the plain MVRNN model, the number of parameters are much larger, because we are using, for every word, we're actually using another matrix in addition to the vector representation, the vector embedding. So that actually adds a lot of parameters. And so this version of it, like recursive neural tensor network, it says it tries to avoid those extra parameters, at least reduce the parameters by allowing like two word or phrase vectors to interact with each other. I'm not really sure what that means. Even the pictures here are not that helpful. So sentiment detection, saying whether a sentence is positive, negative, or neutral. So normally sentiment, like detecting the sentiment, is considered to be easy, but if the text gets too long, we see that the accuracy starts decreasing. Here are some results, some benchmarks. The green bar here indicates a naive-based model, like traditional ML model, and the one in orange is recurrent neural network. The one in blue is for recursive neural networks. We have few more things. Okay. Not all of these things were discussed in the lecture. Yeah, I think that's it for the slides. I actually found like maybe one or two Stack Overflow answers related to this. I'll share those. Let me share. I hope you all can see my browser now. There are some slides here that talk about something related to this. There's not much here. It's just some few points. And here's one Stack Overflow answer, Stack Exchange answer. So yeah, here is just another example. We have a recurrent neural network here, where for every letter, we have 4 letters, HELL, and we take the character embedding for each of these letters, and we pass them to the hidden layer, the hidden state, and it generates its own output state, and the hidden layer's output is passed to the next hidden layer. So this is what we have in a recurrent neural network. And a recursive or tree neural network structure looks something like this. So yeah, I'll be sharing the link for these slides. You can go through them. There's not much here, but there are a few things that can help. Yeah. So we have 2 more lectures after this, and I think they're going to be more like this. I'll see if I can finish them if I can finish them next Saturday. We'll see how that goes. So anything else that you would like to discuss or add, or anything that I missed mentioning, please feel free to say.
So
yeah.
So I I think this class was like, actually, as I said, I think I understood it after your presentation much better. I didn't like the whole I don't know, the whole tone of his lecture was like, well, he invented all this and now it's not used, so it was very pessimistic. So I think it kind of, you know, didn't help. But what I wanted to ask is this. So now they have this new area that's developing pretty rapidly called graph networks.
Mm-hmm.
And I think it's, and I haven't seriously looked into them, but I think it's a very similar kind of idea where you basically like pass information, like you pass information up the tree. I don't know, have you looked at them at all? Do they have like a similar, is it an approach in any way similar to this? Like I've seen a couple of presentations, and basically, but I don't know if that was like mainstream of what graph networks is. But basically, people kind of combine word embeddings and graph embeddings together to basically learn different structures.
Okay, yeah. So even I keep coming across a lot of these things like graph networks and all these on Twitter feed and all, but I haven't really looked into that part yet. But yeah, maybe if they are kind of related to this, maybe that would help us in understanding these tree networks better. I'm not sure though. Like again, I'm more or less, even I felt the same about this lecture. Like it wasn't really that easy to grasp the contents of it, but it just gave a very high level overview of what these tree networks are.
Another question I have, it's different. You know how like you at the end they were showing how they were showing results on sentiment analysis. That's like a standard thing that people do, and I've seen it a couple of times before. People introduce new method and they show how it performs on sentiment analysis, because I guess it's fairly easy, right? Positive, negative. In reality, when somebody wants to use network, they probably want to use it in more difficult and more involved tasks like classification, or like topic modeling, or so. My question is this: so, have you seen any like I don't know if we went into this or not. Have you seen any standards in classification? Um, like yeah, it's easy to determine if document is positive or negative, but is there like a similar thing with classification where you have like, 3 or 4 or 5 classes? Or is it too general? You can't really um, come up with more general,
Okay, so you're asking like for sentiment analysis, we say whether it's
Yeah,
positive or negative.
yeah.
You're
So
saying,
sentiment analysis is a standard binary classification that everybody is using because
yeah,
it's it applies to almost any document. Oh,
yeah.
but have you seen anything similar for classification that's has more than like 1, 2 classes?
Yeah, so let's say we have named entity recognition, right? In that case,
Hmm.
the number of possible classes are much more. Like,
Hmm.
let's say you want to detect. Okay, so we at work are working on something related to named entity recognition, where given a text, it has to automatically extract the entities of interest, like let's say person's name, his date of birth, his current organization. If these are the three things, if you're thinking along these lines, you can add a lot more entities, like maybe his current location. You can add that as well. So this is yeah, this is much more complex problem than sentiment analysis, right? Here the number of classes are more. I don't know whether I'm I don't know whether this relates to the question that you asked.
Yeah, so like I'm kind of looking for like the next standard method that everybody's using to show off their network. And yeah, I've seen a lot of people basically do named entity recognition because
Yeah, yeah.
that,
So when they try to benchmark their model, normally they go for these tasks like NER is one, sentiment analysis, and then we have parts of speech tagging. So these are like the general NLP tasks which the authors normally test their model against and report their findings.
um, so there are no like standard, let's say topic modeling. That's too specific.
Uh, so when you say like standard, so let me like rephrase your question. You're saying if let's say if I come up with some architecture or model and
Mhm.
I want to like publish how good it is, I have to test it on some set of NLP tasks. Only then I'll know, okay, this is doing well or this is doing bad. So for
Mhm.
that, do we have like some specific NLP tasks that we can use for benchmarking our model? Is that the question?
Yeah, and that actually involves topic modeling.
Oh yeah, I think yes. Topic modeling also could be one of those tasks. And I think to answer your question, if we go and see the slides from previous lectures, especially when we discuss different architectures. Like initially we talked about plain RNNs, then we talked about LSTMs, then we talked about sequence to sequence models. So each of these architectures, there were some benchmarks that were reported. So there, I think we will easily get the list of NLP tasks that are normally used for assessing how good these models are.
Mhm.
Yeah,
Okay, thanks.
no problem. Thanks for the questions. So, is there anything else?
I think there is a question on the chat.
Okay, Closet. I think there's a new course. Can we start it again? So, are you talking about CS224 2020, which is like about to start? Oh, yeah. So, even I'm not sure whether they'll be releasing the YouTube videos on the go as they finish them every week, or they might do it all at once. I'm not sure about that, but yes, once I think the new version of CS224 starts, we can plan a study group for that. There is also one NLP course by CMU. Uh, I don't know whether you got a chance, you found it or not. They have YouTube videos for the entire course. I went through like I I was looking for some specific topics and I found these. So maybe we can, yeah. So this is the link. You can just search for CMU NLP. I found them to be good, so we can start this course as well. So yeah, maybe once we are done with this next week, we can do a poll in the channel and then we can start accordingly. And also like I'll be having more time from Feb, so that way I'll be having more time to spend on the study group, both for the assignments or to get more content discussed. So we will discuss that. Um, so CS224 is one option, and then we have CMUs. I didn't go through fast AS and NLP yet, but that's also something that I want to do. But we have a separate study group for that. Uh, so yeah.
Okay, thank you.
Thanks a lot. I'll let you know like what we'll be doing once we're done with this. Thanks for joining today.